Okay, I need you guys to turn to page 41 in your notes booklet. We're looking at the notes on fission and fusion. Okay, and we already talked briefly about, or I introduced briefly, the notion of binding energy of the nucleus. And the binding energy is the energy that is required to hold all the protons and neutrons together in the nucleus. And so the binding energy, which is given the variable E with the little subscript b, binding energy, so just do EB, it's equal to the energy of the nucleons. I hope that lawnmower doesn't get too loud. That's just my husband mowing the lawn. So the energy of the nucleons, and so what that is it's the energy of the protons plus the energy of the neutrons. And so that's energy of the nucleons. So energy of protons, just be proton plus, E plus the energy of the neutrons. So if you take all the energy that's associated with the protons and add it to all the energy that's associated with the neutrons, and that gives you the energy of the nucleons. And then if you subtract from that the energy of the nucleus, then that energy of the nucleons minus the energy of the nucleus, that's binding energy. Okay, that's the energy that's required to hold all the protons and neutrons together in the nucleus. And what comes from this, because the way that we find the energy of the nucleons and the energy of the nucleus is we look at mass energy equivalence. And mass energy equivalence was something that was established by Einstein. Okay, and so nuclear reactions sometimes involve changes between mass and energy. Basically what Einstein said was that mass is energy and energy is mass. They convert to one another. So missing mass always ends up as energy and vice versa. So the formula for that, for the Einstein's mass energy equivalence, is delta E, so change in energy, is equal to change in mass times c squared. Okay, so that means the speed of light to the power of 2. Mass is always in kilograms, and this will give you energy in joules because it's a standard international formula. So it won't give you energy in electron volts. You would have to convert to electron volts to get it into electron volts. So just do a couple quick examples using that formula. So determine the energy equivalent for 1.1122 times 10 to the negative 29 kilograms of mass. And notice this is a really, really tiny amount of mass. Okay? And the whole concept, one of the concepts behind Einstein's mass energy equivalence is that a tiny amount of mass corresponds to a rather large amount of energy, which is the whole basis of fission, like a nuclear fission reaction, or like a fission reactor to get energy, or even an atomic bomb, really. That's the theory behind it, or why it works the way it does. So delta E equals delta M c squared. Okay, so that's, we take the mass, 1.1122, and notice also like the number of decimal places. That's actually pretty typical in the change in mass that you're going to use in this formula. It tends to have a number of decimal places because you want to not lose any precision in that measurement until you round at the very end. Okay, so 1.1122 times 10 to the negative 29 kilograms times 3.00 times 10 to the 8 meters per second, and that's squared. Okay, so probably the most common mistake made here, apart from conversions between joules and electron volts, is forgetting to square the speed of light. And the fact that you're taking a really, really tiny amount of mass and multiplying it by times 10 to the power of 8 squared, so times 10 to the 16, that's why you end up with such a large amount of energy. So in joules, this is 1.00 times 10 to the 12 joules. Sorry, negative 12 joules. And if we want to get that in electron volts, then what we have to do is we have to multiply joules, or sorry, divide joules by the conversion factor between joules and electron volts. So 1.00 times 10 to negative 12 joules divided by, from the formula sheet, 1.60 times 10 to the negative 19 joules per electron volt. And so then that, right, the joules end up canceling, right, and you're left with, so the joules cancel as units, and you're left with electron volts as your unit. And this should give you 6.26 times 10 to the 6 electron volts. And I am doing 3 sig digs because my speed of light has 3 significant digits in it there. Even though my mass had 5 sig digs, speed of light as a constant is 3 significant digits. Okay, so having to do a little bit of conversions and stuff like that between joules and electron volts, which is something you've had to do in the last few units, and then also use that formula. And this is, we're just practicing, because we're going to be using the formula to actually with something called mass defect. So just a little bit of rearranging here. A nuclear reaction produces 9.0 times 10 to the 11 joules of heat energy because of the conversion of mass into energy. What mass was converted into energy? So we're just going to rearrange the formula. Delta E equals delta MC squared. We're going to rearrange it to solve for mass. So delta M is equal to delta E over C squared, which is 9.0 times 10 to the 11 joules divided by 3.00, oops, I ended up with a line there instead of a decimal, but that should be decimal, times 10 to the 8 meters per second. And that's squared, right? Don't forget the squared. Okay, and that will give you 1.0 times 10 to the negative 5 kilograms. And just in terms of units, right? Remember, a joule is a joule is a kilogram times a meter squared per second squared. Right? So then the meter squared per second squared cancels, and you're just left with kilograms. Okay, so that's just introducing that formula, which is a pretty straightforward formula to use. It's what we have to do before generally using that formula that requires a little bit more work. So there's this thing called mass defect, okay? And mass defect is basically it's because if you take the mass of the nucleus and then you compare it to the mass of all the protons and neutrons in the nucleus, so the total mass of all the nucleons, right? So that's the mass of the protons plus the mass of the neutrons. There's a difference. Okay, if you added up, if you took all the protons in the nucleus and found the total mass, and took all the neutrons in the nucleus and found the total mass, and added it all together, that number would be bigger than the mass of the nucleus, and that difference is what's called the mass defect, and that is then that mass defect is equivalent to the binding energy that's required to hold the nucleus together. So the difference between the sum of the masses of the separate nucleons, so the mass of all the protons plus the mass of all the neutrons, and the mass of the nucleus, which is the atomic mass, is called the mass defect. Okay, mass defect is the delta M. Okay, so delta M is equal to the mass of the nucleons minus the mass of the nucleus. And then if you find the energy equivalent of that, then what you found is the binding energy. How much energy is going into holding the nucleus together. So mass defect is the mass that has been converted to binding energy required to hold the neutrons and protons together in the nucleus. And let's remember that the mass of the nucleons is the mass of all the protons plus the mass of all the neutrons. And so then this delta M equals mass of the nucleons minus mass of the nucleus. It's very similar to this. Binding energy is equal to energy of the nucleons minus energy of the nucleus. So this can be done with mass, and basically it would be, you know, mc squared, mc squared, mc squared, right? And then you're finding it that way. Okay, and unless otherwise told, use the mass of the neutron and the mass of the proton off the formula sheet. And on your formula sheet, a mass of a proton and a mass of a neutron are the same. Right, so the mass of the proton is 1.67 times 10 to the negative 27 kilograms. Okay, and the mass of a neutron is the same. Oh, my writing is just terrible. It's hard with the mouse. So in some problems, you're going to be given a different mass. And you'll be given it to 4 decimal places, and then when you're given the mass to 4 decimal places, actually there's a big difference between protons and neutrons. So what we have here is a nucleus of nitrogen-15 has a mass of 2.49 times 10 to the negative 26 kilograms. Okay, so that's the mass of the nucleus here. So the mass of the nucleus of that particular atom or isotope is 2.49 times 10 to the negative 26 kilograms. Okay, and nitrogen-15, so that's 15 is the atomic mass number, so that's the total number of nucleons. The atomic symbol is N, and there are 7 protons. So in this particular nucleus, we have 7 protons and 8 neutrons. And even though the mass of them is the same, I'm going to treat them separately just so that you see the process to take if you have a different mass. And I think I'm going to try and do this in a text box because I've got a lot of writing, and I think it'll just be easier if I use a text box. We'll see how that works. Okay. So I will start. Okay, so the mass of the protons is equal to 7 times 1.67 times 10 to the negative 27 kilograms. Okay, and that's equal to 1.169 times 10 to the negative 26 kilograms. So that's the mass of the protons. Okay. Mass of the neutrons is equal to 8 times 1.67 times 10 to the negative 27 kilograms. Oops. Let's figure this out. There we go. Kilograms. Okay, and so that's equal to 1.336 times 10 to the negative 26 kilograms. Now, you could have done this too, right? Like, and because what I'm going to do now is I'm going to go mass of the nucleons. Okay, which is equal to mass of the protons plus mass of the neutrons, which is equal to the sum of those two numbers that I just found. So 1.169 times 10 to the negative 26 kilograms plus 1.336 times 10 to the negative 26 kilograms, and that will equal 2.505 times 10 to the negative 26 kilograms. And notice that I'm keeping everything to 3 decimal places. So you could have gotten this same number, this 2.25, this number here. You could have gotten that same number by taking 7 plus 8, so 15 times 1.67 times 10 to the negative 27 kilograms. That is a little shortcut. I'm just showing it this way because sometimes you end up with 2 more decimal places here and 2 more decimal places here. So then you have to do them separately. If you're given in the question a different mass for protons than neutrons, you have to do them separately. Okay, so this is the mass of the nucleons, right? So then the mass defect, so I'm gonna put mass and then defect because I can't make I'm not entirely sure how to get a symbol in here. Okay, so mass defect is equal to, just actually go down a little bit and go in. So it's equal to the mass of the nucleons minus the mass of the nucleus. Now, if you mix it up and you do it the other way around, all that's going to happen is you're going to get a negative number for mass, and that's fine. Just do absolute value. Okay, and so then this is equal to the mass of the nucleons that we just found on the previous line, so 2.505 times 10 to the negative 26 kilograms, minus the mass of the nucleus that we were given in the problem, 2.49 times 10 to the negative 26. And you can see it's not going to be a huge difference in mass, right? It's going to be a very, very small number. Okay, and that's going to equal 1.5 times 10 to the negative 28 kilograms. And so that's the mass defect. And so this was part A, what we found here. So this is A. Okay. And we'll do B. Now, what we want to know is the binding energy of the nucleus. So the binding energy is energy, and that would normally be delta E. So I'm just going to put E here. E binding is equal to the mass defect. So mass defect times C squared. Okay, and so then that is, we take our mass defect, we found 1.5 times 10 to the negative 28. And I actually think there was more decimal place, or there weren't more decimal places there. It actually rounded to 1.5, because otherwise you would take more decimal places. With your mass defect, you keep it to as many decimal places as you've been carrying the other things there. So 1.5 times 10 to the negative 25 kilograms times 3.00 times 10 to the 8 meters per second squared. Okay, and then that gives you 1.35 times 10 to the negative 11 joules, which is actually a significant amount of energy. It's times 10 to the 11 joules, but joule is a very big unit, so we don't need very many of them to describe energy. Okay, and so that's binding energy and mass defect. We talk about this with fission and fusion because it's usually with fission and fusion that we're trying to figure out how much energy is released in a nuclear reaction. And so that's typically where you're going to find binding energy. Although there's examples in your workbook that are just strictly finding for just different isotopes. Okay, so next page. Talking about fission, I'm just going to scoot back a page here so I can go back to my pen, and I want to make sure that I have a thin line again. So that's going to be there. Okay, and it's going to go back to full screen. Okay, so fission is splitting of a heavy nucleus into 2 smaller atoms, and in the process you release a very tremendous amount of energy. So fission is what occurs in a nuclear power plant, and it's also what occurs in a nuclear bomb. And it tends to only occur in nuclei that have an atomic mass number, so total number of protons and neutrons, greater than 120. Because those nuclei have a much, much lower binding energy per nucleon, which makes it easier to split the atom. And it was discovered in about 1939 by 4 German scientists, and they discovered that uranium-236 would become extremely, or 235, would become really, really unstable if you forced it to gain an extra neutron to become uranium-236. And uranium-236 was so unstable that it immediately split to form 2 smaller atoms, a bunch more neutrons, and a huge amount of energy. And the released nuclei have a greater binding energy per nucleon because then their atomic mass numbers are smaller. So then that makes them a little bit more stable. Doesn't mean they're not radioactive, but it means they're more stable. So these are just 2 common reactions. And I'm gonna I'll let you know, you will never have to create a fission reaction on your own, or fusion for that matter, because there's no real easy way to predict what the products are going to be or what the daughter nuclei are going to be. You will have to balance them, which is what these are here, right? Like we're missing something here. We don't know how many neutrons we have here. And then in this one, we don't know what the second daughter nucleus is. So you'll merely have to balance them or write them given the description of which isotopes you're dealing with here. So these are 2 common reactions. So here we have uranium-235. It's bombarded with a neutron. It momentarily becomes uranium-236. And then immediately, upon gaining that extra neutron, it splits into barium-141 and krypton-92. So all we want to do is figure out, we've got, like, using conservation of nucleons. And so conservation of nucleons, and I don't have my formula sheet to remember what principle that is, but it's either 7 or 8, says that we've got 1 plus 235. You can also use this one here, but this is just an intermediate one. We don't actually have to look at this in the middle now. We're strictly balancing this side with this side, although it could be this side and that side. So we have 236 nucleons, right? So our top number needs to be 236. That's what that was. It's a 3 there. So on this side here, we've got 141 plus 92. Okay. And that gives us 233 is what we have there. So in order to make this 236, we have to have 3 more nucleons, which means we get 3 neutrons out of this, right? Because 3 times 1 gives us the 3, plus 233 gives us 236. And we should be balanced on the bottom. We have 0 and 92, so we have 92 protons. And on this side, we've got 56 plus 36 neutrons. So then that's 92. Okay. And then notice that this also says a huge amount. It says energy. And that energy is a very large amount of energy, which is why these reactions are important. Okay, again, we have the same thing here. We've got uranium-235 bombarded by a neutron, becomes momentarily uranium-236, so we have 236 nucleons and 92 protons. We have xenon-140, so we have 140 here. We don't know what this one is, but we also have 2 neutrons, so that gives us 142. Sorry, plus 2 equals 142. There we go. We got that right now. Okay. So if we do 236 minus 142, then that's going to give us 94. Okay. So 94 is the number of nucleons we have here. We still don't know what the element is, though. We need to know the number of protons to find out what the element is. So this is 94. And we have 54 plus 0. Okay, so we have 54 protons so far. So we need to find out how many more we need. So we have 92 minus 54, which is going to be, so 90, looks like 38. Okay. So 38 is the number of protons, so 38 becomes our Z. So then we're using conservation of charge. So it's conservation of nucleons when you do the top number. It's conservation of charge when you do the bottom number, because this one has a charge of positive 92 This needs to have positive 92 on this side. And then you would look up element 38 on your periodic table to find what the element symbol is, and it's strontium. That's what that is. Just double check that I actually have that right. Strontium. Okay, so we have 140 plus 94 is 234, plus 2 is 236 on top, and we have 54 plus 38, which is 92 on the bottom, and we're balanced. And generally, you can, in a fission reaction, you can have up to 5 neutrons ejected in a fission reaction. Because notice that's what's happening here. You hit it with 1 neutron, it becomes uranium-236, it immediately breaks apart, and in this case we had 3 neutrons, in this case we had 2 neutrons. You can get up to 5. The average is 2.5 neutrons. And these extra neutrons allow fission to continue. It's kind of continuous. It becomes sort of a chain reaction. So you have this fission reaction, you get 3 neutrons. That goes on to do 3 more fission reactions. Maybe each of those has 3 neutrons. That gives you 9, and so on. So one reaction causes more reactions to happen in a row for as long as there's uranium. And there is a picture to illustrate this on the next page down here. So this shows you uranium-235 hit with 1 neutron. It becomes krypton and barium, and then in that process releases 3 more neutrons there. Okay, so each of those neutrons goes on to hit another uranium-235 nucleus, okay, over here. So then what that does, nucleus, and what that does then is you've got barium and krypton again, 3 more neutrons. So basically you've got 1 neutron, then you have a reaction, you end up with 3 neutrons, then you have a reaction, you end up with 9 neutrons, right? Then you have another reaction, 1 reaction gives you 3 neutrons, 3 more reactions gives you 3 neutrons each, which is 9. 9 more reactions is going to give you 3 neutrons each, which is 27. 27 reactions gives you 3 neutrons each, which is 81. And you can start to see how this might get out of control. So fission is also used in atomic bombs. An uncontrolled chain reaction gives you this exponential growth over and over and over again. And what that is called is going supercritical. So an atomic bomb, as well as a nuclear meltdown at a nuclear reactor, is when this happens, when it gets completely out of control. Notice we've got control rods here. We'll talk in a minute about what those control rods do. Nuclear fission is used in nuclear power plants in what's called a controlled chain reaction. And in a controlled chain reaction, you need to use a moderator, which is used to slow down the neutrons. So that's when this will go supercritical if these neutrons that were produced in each reaction were just moving too fast to be controlled. Then that becomes supercritical. So they use something, either heavy water or a control rod, and that's used to slow down the neutrons released in the fission process so they can be absorbed by the next uranium-235 in the chain. Control rods are used to control the reaction. If the reaction is going supercritical, the rods are dropped further into the core, and what they do is they then absorb extra neutrons, and that slows the reaction down. Fission is really easy to do, but this is the problem. It leaves behind a lot of nuclear waste that needs to be stored for thousands of years. And right now, we don't have, in Canada or in most places in the world, there isn't really a good plan in place for how to store that nuclear waste. So that's probably the biggest detriment about a nuclear power plant, or the biggest disadvantage about a nuclear power plant. I believe that what we were doing in Canada was once the stuff became less radioactive, because the power plants will hold it underwater. They hold the byproducts underwater for a period of 20 or so years until they become less radioactive. And I think then it was just kind of buried in the Canadian Shield, which is a little bit like The Simpsons, like Mr. Burns just sticking the radioactive waste in the trees. But anyway. And then this is the other thing that a lot of people don't know, that some of the nuclear waste, so some of the stuff like nuclear waste would be the barium and the krypton, right? Because those are still radioactive elements. They're medical isotopes that are supplied to hospitals that are used for diagnosing and treating cancer. So if we stopped all of our nuclear power plants, we would lose a lot of the technology we have in the medical field for dealing with a lot of serious diseases. So a lot of people don't know that. And in fact, I think it was the Chalk River nuclear power plant went offline. So a power plant in Ontario went offline for five years or so, and the world supply of medical isotopes was in danger of being completely depleted because of that, because that was what that plant was supplying. Okay, fusion. Fusion is, okay, so just to go back here, fission is splitting. Okay, fission is splitting. can start to hear my nose really starting to stuff up here. Okay, fission is splitting. Fusion is fusing, which is what the word is there. Okay, and fusion occurs when two low mass nuclei, so usually the atomic number has to be under 60, combine to form a nucleus that's more tightly bound. So a nucleus that has a higher binding energy per nucleon. And again, you have to balance. You have to balance the nucleons, balance the protons. So here we've got 4 nucleons, 2 protons. We need to have 4 nucleons. We've got 1, so this has to have 3. Okay, and this has 0 protons, so this one has to have 2. So we have 3 nucleons, 2 protons. So 2 protons, 1 neutron, and this is helium, is what this would be. Okay, and you get a tremendous amount of energy. Way more energy in fusion than in fission, which is why there's been a lot of research into it. It is the reaction that occurs in the core of the sun, and this one here actually is one of the reactions that occurs in the core of the sun. Is just when 2 hydrogen isotopes combine to form helium. You get a lot of energy. This just shows it, although this one shows it with hydrogen 3 and hydrogen 2, so then you actually get like an alpha particle there and a neutron, but you get like a very, very large amount of energy. So fusion can only occur at very high speeds under very high temperatures. So we're talking 400 million or 40 million to 400 million kelvins. It's a reaction that occurs in the sun's core. Been a lot of research into this technology as an energy source, but right now the reactors that they build, the fusion reactors, require more input energy than what they actually get out. But there is a belief that we will at one point be able to do controlled fusion. And if we could do that, one fusion reaction would give enough energy. One single fusion reaction would probably give enough energy to supply something like the US with electricity for an entire year. And that's why there is so much interest in that. So we're going to do a binding energy and mass energy equivalence for a fission reaction here. So the same calculation we did on the previous page, but we're going to do it for fission instead of just a single isotope. I'm just going to pause this one. Okay, that's a bit better. Okay, so the binding energy per nucleon increases in value as your atomic mass number approaches 58. Then it decreases in value as the atomic mass number gets larger than 62. And as a result of that change in binding energy, fission and fusion can only occur in nuclei with specific numbers of nucleons. Controlled fission and fusion reactions produce much more energy than normal radioactive decay. And for both fission and fusion, the energy that's released corresponds to the mass that the energy, to the mass that the reaction transforms into energy. So it's delta E equals delta MC squared. Okay. So, what we want to find here, we've got this reaction here, and again, I think I'm just going to do this in the text box again. Given the following atomic masses, determine the energy produced during the following reaction. So what we have is this is going to be our before. Okay. So basically, what we're doing up here is, if we look at this, we're going to have mass initial. The mass change in mass is going to be the initial mass minus the final mass, which I know is kind of backwards. Usually it's final minus initial. And we could do final minus initial, we just have to do absolute value. But basically we're looking for the change in mass, the change, the difference. And initials, this is going to be more mass initially, so that's more mass. This is going to be less mass. And then this is the mass equivalent here, whatever the change in mass in here is what corresponds to that delta E. That's what we're looking for here. So this needs is 6 squared. Okay, and we have these masses that we're going to use here. So text box, easier to play. Okay, so what we want to find is the mass of the reactants, which is the mass before, right? So this is before, is what we're looking at here. Okay, and so the mass of the reactants is going to be the mass of uranium, so the mass of a neutron, plus the mass of uranium. which is the mass of a neutron is 1.6749 times 10 to the negative 27. Okay, notice this is one where you're given the mass of a neutron, and you have to use it instead of using just 1.67 from the formula sheet. So 1.6749 times 10 to the negative 27 kilograms plus 3.9029 times 10 to the negative 25. Again, those of you that have taken Science 30, you guys did this in Science 30. Okay, and that equals 3.919649. So notice the number of decimal places I'm taking it to. Times 10 to the negative 25 kilograms. Okay, and the mass of the products, which is the after, is equal to the mass of barium plus the mass of krypton plus the mass of 3 neutrons. Okay, so make sure you get that 3 in there, right? Because it's 3 neutrons in the formula. So the mass of barium is 2.3898 times 10 to the negative 25 kilograms, plus the mass of krypton, which is 1.4765 times 10 to the negative 25 kilograms, plus 3 times the mass of a proton, 1.6749 times 10 to the negative 27 kilograms. Just stretch this a little, maybe that over there. Okay, and so then that equals, so we'll just go over here. Okay, and so then that should equal 3.916547 times 10 to the negative 25. And it's actually really easy to end up with the wrong number here and make a mistake. Okay, so the change in mass, so we'll say, I wish I could get a delta in there, I just can't. I don't think I can. Oh, okay, so the mass, and I'll say change in, so the mass change is equal to the mass of the products, so reactants, minus the mass of the products. Which is 3.919649 times 10 to the negative 25 kilograms minus 3.916547 times 10 to the negative 25 kilograms which is equal to 3.102 times 10 to the negative 28. Sorry guys, kilograms. And then we want to find, what we're actually trying to find is the energy produced. So that energy, so E is equal to mc squared, which is equal to 3.102 times 10 to the negative 28 kilograms times 3.00 times 10 to the 8 meters per second squared, which is equal to 2.79 times 10 to the negative 11 joules. Ow! Oops. Okay, let's go back there. Let's fix that. Close. 2.79 times 10 to the negative 11 joules. And that is how you find the energy released in a nuclear reaction. Just the same as using your mass defect. And what you're going to work on, and this is on for Tuesday, right? So depending on when you're watching this video, this is for on Tuesday when you will have a sub while I am in Red Deer with my tennis team. There's some workbook questions that you can work on, as well as working on your unit assignment. So in your workbook, it is page 330 to 331. This is just fission and fusion stuff, and this is number questions 1 to 5. There's not much in there, so this is fission and fusion. Let's do fission and fusion. Ooh, my writing is delightful. And this next one is on mass defect. Oh, look at that. Cursive with the mouse. Okay, and that is in your workbook, and that is on, that's just the following pages, so page 333 to 337, numbers 1 to 13. And we're almost done the unit. We have 2 kind of quick lessons, 1 to 13, that is. Okay, guys, I will, well, I guess I'm going to see a lot of you on Monday in West Ed, but otherwise I'll see you Wednesday.